Hello there. Welcome to the session 3 of Unit 2. And for this session, we'll be looking at the latent heat of evaporation. Let's look at the objectives. There are two objectives here, and the first one is to be able to define specific latent heat of evaporation. The second objective here is to be able to describe an experiment to determine the specific heat of evaporation. At this stage, there are two particular terminologies that we have to note here. That is evaporation and boiling. And with their differences, they have one common similarity between them. And it is both processes are liquid to gas changes, right? And with their differences, we have two differences for the evaporation and boiling. So the first point is that for evaporation, it involves the law of liquid molecules from the surface region only and can take place at any temperature. And a rare example is the diagram that it has been shown here, where for the evaporation we expect that the molecules should occur only at the surface here, and it doesn't depend on the particular constant temperature, let's say 100 degrees. So say at 95 degrees, at 80 degrees, at 60 degrees, and evaporation is expected to occur. Let's look at boiling. And boiling here is a bulk phenomenon where molecules are lost from the whole body of a liquid. Yes, it's a transition of liquid to vapor. But this time around, it's not only the surface that is occurring, right? It occurs on the whole body of the liquid. And the last point is no definite temperature. That is for evaporation. It has no definite temperature. As compared to the boiling, it occurs at a definite temperature. So for boiling, we expect that a boiling point should be reached before it starts boiling. But for the evaporation, it doesn't have evaporation point. At any point, evaporation is set to occur, where the molecules at the surface tend to take place. Let's look at specific heat of evaporation here, and it's defined as the quantity of heat energy required to convert a unit mass of liquid into vapor at the same temperature. Unlike the specific heat of fusion that we did in the previous section, where we expect that a quantity of mass is converts a unit mass of a solid to a liquid. This time around is from a liquid to a vapor. And the formula that we have here is Q equals M of LV, where Q here is our energy, M here is our mass, and the LV here is the specific heat of evaporation. So in case we are calculating for the specific heat of evaporation, we just have to make the LV the subject, where the LV right now becomes LV equals Q on on M, right? Where this one becomes the mass of the particular substance, and Q here becomes the energy, right? And the LV here becomes the specific heat capacity, specific latent heat of evaporation. The unit here is joule per kilogram. So the Q here represents a joule, and the M here represents a kilogram. We have to take note of the units very well. So in case you are given a question and the mass here is given in grams, from our previous dimension analysis that we've learned in general physics, you should be able to convert the gram to kilogram. In case it's given in megagram or hectagram, any prefix that is given, you should be able to convert it before you do your calculation. Let's look at how we are able to determine the specific latent heat of evaporation by method of mixtures. And this one, we are also going to use the principle of conservation of energy, where we know that the heat loss is always equal to the heat gain, right? And let's look at the setup that we have here. It's a little bit complicated but a little bit simple too. So here we have our stirrer inside here in our calorimeter. This is our calorimeter. And we have what? An insulating what? Support, which is also what? In a jacket. Most of the times the calorimeter is made of copper. We also have a boiler here at the top here, where a heat is being what? Applied to it. So for this particular place, we expect that there should be an evaporation here, right? To liquid to a vapor, which is going to be trapped in a what? In a liquid trap here, and later on comes here, where we have a particular temperature, a thermometer here, to be taking the temperature as it changes regularly. Here we have our heat gain here, heat loss here, to become the MWCW plus the CC in a bracket T1 minus T2. The heat loss here right now is the mass of the water, the mass of the specific heat capacity of the water, the mass of the calorimeter, and the specific heat capacity of the calorimeter. Then their temperature differences equals the specific latent heat of evaporation, our mass, the mass of the water, and also the mass of the water that we have here. Note, there are two different waters that we have here, and their temperature changes. So depending on what we want to calculate, say this particular Kelvin, the specific latent heat of evaporation, we just make this one the subject by sending the whole term here to the other side, and after that dividing the whole term by m, so that our Kelvin will stand alone.